Okay, thanks for the introduction. I'm going to, shift gears here a little bit and talk about catalysis from an electronic structure perspective, specifically the oxygen evolution reaction and a robust, one of the most robust catalysts for doing that under alkaline conditions. So let me just start by briefly motivating the catalysis of that specific chemistry to this audience. Oxygen evolution is part of, for example, what you would require for a hydrogen fuel cell, specifically on the fuel storage side, your fuels being hydrogen and oxygen. So when you burn hydrogen and oxygen, you get water, and you would ideally like to turn that water back into your solar fuels, as some people like to call them, those being hydrogen and oxygen. And of course, that's a difficult reaction to do because luckily water and oxygen are very stable molecules, and the transformation between them should be very difficult. So we're going to need to rely on catalysts for doing that, electrocatalysts more specifically, and we would like them to be earth abundant and cheap materials on top of that. And of course we want to do this in a fashion that gives you high turnover frequencies with high stabilities and at low overpotentials with high selectivity. So this is the couple schematics of the system I'm going to talk about today. I'll call it nickel iron oxyhydroxide. More accurately, it's an iron-doped nickel oxyhydroxide material. And it deposits at least under reasonable applied potentials as these single metal or metal octahedral sheets that becomes intercalated by both solvent and electrolyte ions. And you can see the nickel and iron sites octahedrally coordinated by oxygen, and then there's a significant degree of protonation on the oxygens that sort of point up and down between the layers. This isn't the only example of this type of system. Actually, a lot of those third row transition metals and combinations of them can form these type of what some people call layered double hydroxides. When you oxidize them and deprotonate them, they become oxyhydroxides more accurately. So let me take a step back now and just say that actually nickel electrolyzers, as they have been called for many years, are kind of an old solution to doing this water splitting or oxygen evolution reaction. So this is a paper from the 70s about nickel electrolyzers in alkaline solutions. And this is a paper from 1987 that actually even understood the effects of the iron doping as to its enhancement of the catalytic activity of the material. But it's important to note that as new both computational and experimental techniques emerge, and of course our invigorated interest in renewable energy technologies, we need to take a look at what works and why it works, and how we can reasonably improve on what works. So some more recent work on this and related systems. This, I believe, is from 2014. You can see, and this is a plot of overpotential versus current density. You can see the green trace here is in the absence of iron. It takes a lot more potential to get a lot less catalytic current. Catalytic current takes off way over here. And actually, funny enough, even the accidental inclusion of iron impurities or iron dopants gives you a very significant increase in catalytic activity at lower overpotentials. And then the more intentional 5 or 25% iron doping gives you what appears to be the optimal or maximum catalytic activity for this material. And 25 seems to be the optimal iron loading for OER catalysis. So there was a joint experimental computational paper shortly after these experiments were published that claimed that under working conditions, the active site, oxygen evolution active site for this material was an iron 3 site. However, shortly thereafter, the group of Shannon Stahl at Wisconsin-Madison, who we ended up collaborating with, did a operando Mossbauer spectroscopy experiment where they did Mossbauer spectroscopy under the working electrocatalytic conditions, and they saw a steady state and significant population of iron 4 under those working conditions, which of course directly contradicted the previous study predicting iron 3 as the active site. And there's been some other computational work as well in more qualitative ways documenting the sensitivity of the metal oxidation states to the protonation and oxidation state of the material as well. So we're not the first to take a computational look at this system. Before I get to how we did that, let me just briefly state the objectives we set out for ourselves. So we first want to understand the redox activity of the material, what the various peaks in the cyclic voltammogram represent on a very microscopic level, atomistic level. We wanted to try to determine what the metal oxidation states are in the material, which of course, if you're from the materials electronic structure community, could be a little bit of a controversial statement, but we think we have some good qualitative tools for doing that. And then because we're going to do electronic structure calculations, we want to see what that looks like at an atomistic level, try to glean some insights about the chemistry and the catalysis that this material does so well. Okay, so briefly on the methodologies, at least computational methodologies, we did a periodic boundary condition, plane wave-based DFT calculation using the open source Quantum Espresso suite. And we optimized the geometries for this material at a DFT plus U, or GGA plus U level of theory, which gave us good bond lengths in comparison to X-ray experiments. However, it turns out that we needed a higher level of DFT treatment, at least, known as a hybrid functional, PB0 being the one we used, to get the qualitatively correct electronic structure for the material, both the nickel and iron doped materials. Nickel and iron oxides are sort of pathological cases where GGA functionals break down in terms of opening up a band gap. There are these plus U approaches seem to help for the bulk oxides, but for whatever reason, and we think it's the significant oxygen nature around the Fermi level, we needed these hybrid functionals, which are of course significantly more computationally intensive than the GGA plus U types, to open up an appropriate band gap to then thereafter do some redox thermodynamics and look at the oxidation states. So I mentioned redox thermodynamics. We developed a thermodynamic scheme to cancel out all the error or cancel out all the terms that we wouldn't be able to get from fairly standard electronic structure calculations in order to get those redox potentials, which I'll show you on the next slide, I believe. And we were actually able to get away with using the magnetization, the individual site magnetization on all the metals in our unit cell as a sort of qualitative benchmark for oxidation state, and I'll show you a little bit more about that. And then very briefly, at least for the bulk metal sites, we were able to get away with a 4 metal unit cell. Of course, still fairly expensive calculations given the hybrid functional. I'm going to use a nomenclature of sort of NH, 2H, 8H, 4H, and that is representative of the hydrogenation level of our unit cell. In order to achieve the 25% iron doping, we replaced one of our nickels in the unit cell for iron. So let's revisit those cyclic voltammograms. These were taken by our collaborators at Wisconsin. So let's follow the black trace first. First, you see this reversible feature around 0.53 volts versus NHE. And this is well known in the experimental community to be the nickel 2 to nickel 3 oxidation, or equivalently the hydroxide to oxyhydroxide transformation of the material. So we set this as our reference potential. So this would be in our unit cell 8H to 4H, 8H being the hydroxide stoichiometry, 4H being the true oxyhydroxide stoichiometry. And then if we ramp up when the experimentalists ramp up the applied potential here, you see a little bit of a shoulder that immediately precedes the onset of catalytic current for the pure nickel material. And we assign this shoulder that immediately precedes catalysis to this 4H to 2H transition. We compute a redox potential of about 0.73 volts right around that shoulder. And I'll tell you what that means more chemically speaking in the next slide, I believe. But let's switch gears first to the iron dope trace. you see that this reversible feature gets washed out now by the earlier onset of catalytic current in the case of 25% iron doping on this red trace here. First of all, the 8H to 7H transformation occurs well negative of what they can even observe experimentally. So we're starting from 7H here as our reactant. And we have 5 fairly close in energy, at least given error bars in DFT, candidates for that transformation associated right at the onset of catalytic current for the iron-doped case. And I'll get into what those mean in terms of oxidation states. So I mentioned we use the magnetism on each metal site as a proxy for oxidation state. And we sort of derived this from a idealized inorganic chemistry d orbital octahedral field model, where nickel-2, you see before you pull off any of the protons and electrons from your unit cell, you have 4 uniformly magnetic nickel sites, which we assigned to be nickel-2 in the hydroxide. I showed you the reversible trace on the black cyclic voltammogram here, which gets us to 4 uniformly magnetic nickel-3 sites at n equals 4 or 8 minus n equals 4. And then that shoulder, which we assigned to the 4H to 2H transition of the nickel-only material, puts you right here, where you actually have a coexistence of nickel-3 and nickel-4, nickel-4 being having no unpaired electrons or no net magnetism, a coexistence of nickel-3 and nickel-4 under what we can assume to be the catalytically working potentials. So you can see sort of the subsequent deprotonation and oxidation of the nickel-only material affecting the redox character of the individual metal sites. Now we take a look at the slightly more complicated iron-doped picture. I mentioned we start at n equals 7 or 8 minus n equals 1 here, where iron is sort of pre-oxidized to the 3 plus oxidation state. At least that's where it's most happy, with a full complement of nickel-2. And then those 5 red numbers I showed you alongside the cyclic voltammogram are representative of these 5 vertical slices of the plot here, all of which contain iron in the 4 plus oxidation state with a coexistence. And of course, these are, because of the redox potentials, they're thermodynamically very close in energy. Nickels between the 2 plus and 4 plus oxidation states. But the rub here is that any of those oxidations associated with the onset of catalysis for the iron-doped system will give you iron in the 4 plus oxidation state, which seems to corroborate the Operando-Mossbauer experiments that our collaborators had done previously. So because we've done these nice electronic structure calculations, let's try to make some, try to infer something about catalysis, at least from this bulk calculation, or 2D bulk, I should say. You can see these plots, if you're unfamiliar, are projected density of states plots, where the dashed line here is representative of the Fermi level of the material. Anything to the left is the valence band or the filled electronic states, if you're more of a chemist. Anything to the right is the conduction band or the unoccupied or virtual orbitals for the chemists. So we can project this density of states, which is already resolved throughout the K-space. We can project these onto an atomic-like basis set and look at the chemical nature of those frontier orbitals. So we can break this down in a number of ways. First, by metal oxidation states. So you can see nickel-3, nickel-4, where you can see in the valence band nickel-3 has that extra electron relative to nickel-4, so it shifts it a little bit higher up in the valence band. And then most importantly, if we keep an eye towards catalysis, you can see the oxygens or the oxide motifs, which have been deprotonated in the process of oxidizing the material, sit a little bit lower than their hydroxide counterparts in the conduction band. And we would expect that to be the case because those should be the more sort of nucleophilic sites for an attack by hydroxide or water in the process of the oxygen evolution reaction. Now, we know that iron significantly enhances the catalytic activity of the material, and we can take a look at maybe why that is from the electronic structure. So you can see we can break down the projected density of states by metal oxidation state here, and right here at the bottom of the conduction band, sort of dominating the conduction band minimum, is the iron 4 that we had previously identified. Again, oxides, deprotonated oxygens seem to be a little bit more nucleophilic, And most importantly, the oxygens that are coordinated to this iron 4 site sit selectively at the bottom of the conduction band, meaning that those are likely to be more active sites than their nickel coordinated counterparts. So to summarize what we've learned for this sort of 2D bulk model, we were able to assign all of the peaks on the cyclic voltammogram to redox transitions in the material. We were able to, with a nice qualitative metric, determine the oxidation states of those nickel and iron sites under a range of working applied biases. I didn't talk about the nice experiments that our collaborators did in terms of the spectroelectrochemistry, but they actually showed that under an increasingly anodic potential, you can actually see in the UV vis the redox changes bear out as you can see the material changing in a UV vis manner as the redox changes to the material play out under increasingly anodic potentials. And then we characterized the frontier orbitals or the frontier electronic structure of the material and made some inferences about what that may mean for catalysis. So what is there left to do? And I've sort of been keeping this because if you are familiar with the heterogeneous catalysis community, you probably know that most of the action, most of the catalysis is actually happening not in the bulk, even though our bulk is exposed, in this case, to solvent in electrolytes. It's happening at a very special surface or edge or defect sites in the material. And this came out, I think, shortly after we published on the sort of the interior metal sites, where they can very quickly add an iron 3 salts in the presence of the nickel oxyhydroxide. And very shortly thereafter, you recover basically all of the catalytic activity that you otherwise would get by letting the iron take its time to get into the bulk of the material. And from that, they inferred that iron only has to very quickly get onto the edge of this material, and those become the most active sites for catalysis. That's where all of the action is actually happening. And then there's been some other experimental work where they claim to see very high valence iron intermediates throughout the catalytic reaction. So we figured that we could sort of break the 2D periodicity of the unit cell that we had been using in order to explore these very likely more active sites, which I'll call edge sites. And we can do a sort of similar suite of analyses to get an atomistic understanding of these sites. So this is somewhat of an ongoing work, but I'm going to talk about what I've learned so far. The unit cell, of course, has changed now in that we have broken the periodicity in a different dimension, inserting some vacuum in what is the y dimension arbitrarily. And now you can see we have purposefully under-coordinated metal sites sitting at the edge of the material, and because we have an appropriate breadth of the nanowire, we have characteristically interior and exterior metal sites to study in a similar fashion. And of course, I'd be remiss if I didn't mention that we still want to do the hybrid functional electronic structure characterization of these these broken periodicity, highly asymmetric materials with even larger unit cells than I've shown here, and that is enabled uniquely by the resources on Blue Waters. So just the last piece of data that something that we've already learned about these nanowires. First of all, there's a large energetic preference, large thermodynamic preference for iron to reside actually at those exterior sites rather than in the interior. So maybe it's not a coincidence that very quickly introducing iron to the material recovers all of the catalytic activity, because it's going to prefer thermodynamically to reside at those edge sites anyway. About a 2 eV thermodynamic preference for iron to reside at the exterior rather than the interior. And then even, and on top of that, if you stick iron in the interior in our computational model, you can see that it no longer resides at the conduction band minimum. You can see iron and oxygen characteristic states have taken over that very important, or catalytically very important region of our density of states plot. Whereas when iron is happy at its exterior site, you can see, actually not too easy to see, but you can see dark green and red iron oxide like motifs at our conduction band minimum, inferring that it has taken its rightful place as the catalytically active orbitals, so to speak. So let me just finish by acknowledging various people who helped out with the endeavor. My PI, Sharon Ham-Schiffer. We just moved to Yale from U of I. Aparna is another grad student in our group who helped me with a lot of the bulk, or 2D bulk calculations. Our experimental collaborators, Professor Stahl and his research scientist James at Madison. And then we had a lot of help from materials electronic structure experts at Chicago, Julia Galley and her former postdoc, Martin. And then I should certainly express my gratitude to the Blue Waters Graduate Fellowship Program, as well as my point of contact at Blue Waters, Victor, for help getting Quantum Espresso and the various applications I needed up and running on the system.